I have been waiting for this introduction. It was simply amazing. Thank you very much. In a recent survey, I was asked to describe Radcliffe in 5 words. And this might look like an easy question to answer, but I soon realized it was quite challenging because there are so many words that come to mind. Encouragement, support, diversity, inclusion, recognition, inspiration, motivation, uplift, elevation. Many of these universal values align with the history that happened between these walls and are reflected in the mission of the Institute. Radcliffe is intellectually rigorous, urban in location, bold in spirit, and global in outlook. Radcliffe is about big and important issues and ideas like peace and governance, health and equity, resources and tolerance. Radcliffe transforms, enlightens, and empowers. I would like to highlight that working in this academic constellation has been an immensely intellectually uplifting, professionally rewarding, and personally transforming experience. To be a Radcliffe Fellow is both a great honor and a privilege, and I can't express how grateful I am to the leadership for giving me this opportunity to be part of this. I would also like to take this opportunity and highly recommend to my fellow researchers from natural sciences to apply for this fellowship and to advance professionally in a supportive, stimulating, and very dynamic setting. As Meredith mentioned, I come with a cross-cultural experience, and throughout my 2 decades of academic career, I learned to appreciate both the benefits and challenges of culturally and socially very diverse academic settings. I was born and raised in Macedonia, a beautiful country with a very rich and long history in Southeastern Europe, but also a place which appears to be constantly in transition. I spent half of my professional career in Japan, in an academic environment which is in many ways established and advanced, but which is also generally viewed as rather rigid and conservative. I now work for New York University in their Portal campus located in the Emirates, where one of the best private American universities has set as its mission to partake in the process of transforming an authoritarian society within a very short period of time. I also happen to be the only chemist in this batch of fellows, and when I was thinking about the subject of this talk, the chemist in me was tempted to show you something like this. I can lend you a few slides of this sort if you ever suffer from insomnia to help you with the sleep. But in an attempt to avoid being technical instead, I wanted to take you on a journey and tell you about something all of us can relate to, something that also continues to inspire great scientific discoveries. I asked myself, what is that these so different cultures that I have experienced have in common? In a recent interview for one of the scientific journals, I stated that there are 2 things that inspired me to become a scientist. First, the curiosity, and second, the nature. I recognized very early in life that the full worth and beauty of nature. Instead, my very first recollections of my early childhood are those of the beautiful green hills of Macedonia, where I was both curious and inspired about how plants and animals live and survive. I later discovered that endorsing cognitive connectedness to nature and engaging with natural beauty is not only common for many cultures, regardless of their social and political milieu, but at an individual level, it is also thought to be associated with greater well-being and awareness for environmental conservation. And that idea is perhaps best sublime in this quote of John F. Kennedy that you can find on a board in the Kennedy Memorial Park right here in front of Harvard. But nature also has a quirky, unexpected, or just downright weird side. Geckos can climb up walls and stick to ceilings, insects can walk on water, and some snakes can even fly. These obscure corners of the living world might sound like an episode of the Ripley's Believe It or Not, yet they happen more often than we think about them, and more importantly, they may hold enormous benefits to the humanity. Over the course of millennia, plants and animals have developed and perfected mechanisms for motion, survival, and dispersal with astounding grace, speed, and versatility. But how do they do it, and what can we learn from them? In this next slide, you will see the amazing efficiency, durability, adaptability, and self-healing capability for which the biological systems are endowed. And these are some of the main inspirations of the material scientists as structure functionality principles. And if we look back in time, the living beings had a very, very long time to perfect themselves in order to survive. The age of the Earth is about 4.5 billion years, and the earliest undisputed evidence of life of Earth dates from at least 3.5 billion years ago, although there is also evidence that life began much earlier. The global changes with processes such as plate tectonics and solar variability have occurred over thousands to millions of years. On a much smaller scale, over decades to centuries, the human activities have become an important driver of the physical climate system and the biochemical cycles. To just give you a feel of how long it took the living organisms to evolve to what they are now, insects such as ants have been around since 140 million years ago, while the squid have been on this planet since about 100 million ago. Our human lineage started only about 2 million years ago, and about 200,000 years ago, our species, the Homo sapiens, emerged. So you might want to consider this the next time you step on an ant or have your calamari for dinner. If aliens ever visited our planet and they decided to communicate with humans, one of their first questions would probably be, how many distinct life forms does your planet have? You would be surprised with the uncertainty in our answer, which illustrates our limited progress with this research topic. In more than 250 years since the Swedish biologist Carl Linnaeus began the science of taxonomy, 1.2 million species have been identified and classified. It is estimated that it will take us another 480 years to complete the job. However, the Linnaeus system forms a pyramid-like hierarchy, which is inverted image of the taxonomic rank shown here. The lower the category, the more entities it contains. There are more species than genera, more genera than families, more families than orders, and so on, right up to the top levels, kingdom and domain. Recently, a new method was proposed that allows the total number of species to be predicted based on the consistent scaling pattern among the different levels of the taxonomic classification: system, order, genus, species, and so on. According to the latest biodiversity estimate based on this new method of prediction, there are 8.7 million, give or take 1.3 million eukaryotic species on our planet. This means that a staggering 86% of land species and nearly 91% of marine species remain undiscovered. With these numbers at hand, we cannot even begin to answer questions such as how much diversity we can lose while still maintaining the ecosystem services that humanity depends on. So why are the materials so important? Because about everything you see around you is made of materials. From the concrete walls to the intricate parts of your smartphones, from the smallest grain of sand to most complex systems like the living organisms. And we want these materials to be lighter, thinner, smarter, better. We care about how they look and feel, how long they last, and how much we need to pay to use them. With great enthusiasm and curiosity, material scientists and engineers working in the biomimetic materials research field ask why natural selection may have favored one species over another or one design over another. From the labs of Harvard, here, and MIT, to the deserts of rainforest, they seek to answer to why animals and plants have adapted and evolved to disperse and traverse their environments, taking advantage of physical laws and environmental conditions with results that are both startling and ingenious. Our desire and ability to imitate nature has also continuously evolved, and as technology improves, more difficult challenges are yet to come. The humanity changed forever during the first industrial revolution, which began in Britain in the late 18th century with the design of an engine in which burning coal produced steam which drove a piston. The second industrial revolution came in the early 20th century when Henry Ford mastered the moving assembly line and ushered in the age of mass production. It witnessed the expansion of electricity, petroleum, and steel. The first two industrial revolutions made people richer and more urban. Now a third revolution is underway. Manufacturing is going digital, and a number of remarkable technologies are converging. Clever software, more dexterous robots, new processes, a range of web-based services, and particularly important for all these developments, novel and better materials. Living in the area of emergent hyperconnectivity, we're on the cusp of the fourth industrial revolution, or Industry 4.0. It is quite different than the three industrial revolutions that preceded it because it is posed to challenge even our ideas about what it means to be human. The fourth industrial revolution describes the exponential changes to the way we live, work, and relate to one another due to the adoption of cyber-physical systems, the Internet of Things, and the Internet of Systems. Implementation of smart technologies in our factories and workplaces, connecting machines that will interact with each other, visualize the entire production chain, and make decisions autonomously. This revolution will impact all disciplines, industries, and economies. And again, it requires new, better materials. In parallel with these developments, there have been efforts to develop a global understanding of the functioning of the Earth as a system. The effort necessitated linking knowledge and unifying methodologies and conceptual frameworks from both the physical and biological research domains, and will inevitably result in a highly integrated science and technology realm. One of the motivations for this development is the growing impact of humans on the Earth system, and more importantly, the necessity to provide solutions while also recognizing the impact of the relevant social drivers and their consequences for the changes that are occurring. Materials are derived from natural resources, and materials efficiency has become as important as energy efficiency, with efforts towards a circular materials economy where the materials are reused and to draw down from the natural resources base. One of the critical components in the transferring an idea to application is that of the design. The design is the process of translating an idea into detailed information from which a product can be manufactured. The starting point in the design is a market need, and the end point is the full specification of a solution that fills the needs. While many aspects of the natural principles are beyond our understanding, a significant progress has been made in elucidating the underlying principles. In a highly interdisciplinary exercise, materials scientists and engineers work together to reverse engineer these principles. Making biomimetic materials and systems requires not only understanding of the basic principles, but also modeling, graphic simulation, fabrication of the materials and systems, and ultimately, physical implementation of the resulting technology. But let's go back in time. Perhaps the most famous story related to biomimetics is that of the Swiss inventor Georges de Mestral. In 1941, de Mestral was on a hunting trip and noticed that both his pants and his Irish pointer's hair were covered in the burrs from a burdock plant. Being curious from a very early age, de Mestral decided to study the burrs under a microscope, more out of the curiosity than because of a business opportunity. What de Mestral saw were thousands of tiny hooks that efficiently bound themselves to nearly any fabric. Being inspired by science, de Mestral realized that if he could create a synthetic form of this fabric, it would allow for a new way to fasten things, a middle ground between buttons, zippers, and simply sewing stuff together. His idea was to take the hooks he had seen in the burrs and combine them with simple loops of fabric. The tiny hooks would catch in the loops and things would just come together. In 1958, he was granted a patent for his invention for what would later become known as Velcro. The principles of operation of all biomimetic materials rely on capturing the essence of biogenic systems in an attempt to emulate their functionality by intentional modulation of their structure and composition. The hierarchical and mechanistic traits that enable responses to environmental stimuli are central to the advancement of the biomimetic science as they inspire the design of durable artificial architectures. Some of the principles can be harnessed to make miniature devices that can fly like a dragonfly, adhere to walls like a gecko, adapt in texture, pattern, and shape of the surrounding like octopus, process complex three-dimensional images in real time, recycle power for operation and locomotion, self-replicate or self-repair, grow using surrounding resources, or generate and store energy. Plants, for instance, have prevailed and adapted to different climates by continually perfecting energy-conserving mechanisms for dispersal that utilize spatiotemporal gradients in temperature, light, pressure, and humidity. Some futuristic applications can also be envisaged, such as those that mimic the motility of a tumbleweed. Sophisticated robotic tumbleweed-like devices could use the wind to operate on their own for years, traversing thousands of miles of desertscape using only the wind to send information on the desert conditions. Since Mars has its own wind, which you can hear on this slide, making a rover that has the structure of a tumbleweed is an attractive idea to design a vehicle which can travel great distances with a minimal power. As a second example, this tumbleweed-inspired prototypical mine detonator, on the last picture here, is composed almost entirely of bamboo and biodegradable plastics, with a skeletal structure of spiky plungers that resembles a giant spherical tumbleweed from another planet. Through evolution over millions of years, nature introduced power-efficient solutions that use air or air currents. Mimicking these solutions could improve our lives and the tools we use. Trees disperse their seeds by using aerodynamics principles to passively travel with the aid of wind, and these principles have been used in devices from boomerang to gliders to helicopter blades to aircrafts and drones. Maples, like many long dispersal tree seeds, rely on wind, upward currents, and gusts to spread their seeds over long distances that can reach several kilometers. The winged seed of a maple called Samara auto-gyrates as it falls. The spiral motion is insensitive to the initial conditions and is stable against wind disturbances. So last spring, I actually collected some of these seeds here in front of Radcliffe, and I would like to show you how this happens. So these are the seeds, and if we throw them, they start to rotate for a reason. The interesting point here is, regardless how do you throw them in the air, they've always stabilized their motion and go into perfectly steady descent. So if you throw them, so this is, maple seeds are able to rotate because of their structure, because their center of gravity, which is determined by the position of the heavy nut, is located at the base of the wing-shaped seed. It has been observed that, despite their small size and slow velocities, these seeds are able to generate with lift, being able to remain in the air for longer times than other non-rotating seeds. A main puzzle here has been to understand exactly how the seed settles into their steady descent. This stable auto-rotation of maple seeds or other similar rotary seeds depends on the interplay between their three-dimensional inertial and aerodynamic properties, which result in unexpected high lift forces despite their small size and slow velocity. The generation of so-called stable leading-edge vortex, similar to that observed in hovering insects, bats, and some birds, has been shown to be responsible for such high lift force. Robotic models seeds that have been recently used to accurately predict the presence of a strong tornado-like vortex on top of the maple seed wings that elevates the lift and increases their dispersal distance from the tree. So these lessons learned from the maples and other similar seeds have been already used as technology in the design of unmanned aerial vehicles, quadcopters and drones. The maple seeds, for example, were the inspiration for a new kind of flying machine that could be useful for military information gathering. Lockheed Martin's Intelligent Robotics Laboratories developed an unmanned craft to replicate the motion. The device, named Samurai, has only 2 moving parts and a camera. It can be controlled by a remote control or by an app on a phone. Planet Earth has been called the Blue Planet due to the abundant water on its surface. Water is the most abundant resource in the natural environment, yet about 97% of the total water on Earth is seawater. The fresh water that is directly available to humans makes up only between 0.4 and 2% and comes mainly from frozen glaciers and polar ice caps, liquid groundwater, or aerial humidity. In a recent Global Risks report, water scarcity has been ranked as one of the highest environmental and societal risks. It is estimated that 2/3 of the world population will experience water stress by 2025. Approximately 1 billion people live without access to clean water resources in rural areas of African, Asian, and Latin American countries, turning the issue of water shortage and scarcity into a major global concern. Using an ensemble of climate models and socioeconomic scenarios, the World Resources Institute predicts that 33 countries will face extremely high water stress by 2040. The businesses, farms, and communities in Chile, Estonia, Namibia, and Botswana could face a especially significant increase in water stress by 2040, and these countries will become more vulnerable to water scarcity than they are today. 14 out of 33 most water-stressed countries in 2040 are in the Middle East. The region, already the least water secure in the world, draws heavily upon groundwater and desalinated seawater and faces exceptional water-related challenges for the foreseeable future. With regional violence and political turmoil commanding global attention, the water issue may seem a tangential problem. However, looking into the future, and according to the US National Intelligence Council, the water scarcity will put key North African and Middle Eastern countries at greater risk of instability and state failure, and will distract them from foreign policy engagements with the US. I live in the Emirates, and although this country is only about 45 years old, the main cities here are an urban jungle, very similar to other metropolises like New York City or Shanghai. So if you drive only about 10 kilometers from here, you will encounter the very different environment, the Arabian Desert. And there is no other place on Earth where the contrast between the urban and the natural is so stark. It is the fourth largest desert in the world and the largest in Asia. The climate here is hot and dry, with only about 100 millimeter rainfall per year, miles and miles of nothing but sand and wind. Yet the desert is not a deserted place. In many regions, fog and dew represent regularly occurring phenomena and have a substantial impact on the hydrology and ecology of the local vegetation. Over several billion years of evolution, the nature has helped desert organisms evolve and survive in an extremely hostile and arid environment by harmonizing the structure and function and by making use of minimal resources to attain maximum performance. Can we learn something from these amazing creatures? Meet the Stenocara beetle. I think Annie would love this part. It thrives in the Namib, a coastal desert in southern Africa, one of the most arid habitats on Earth, with less than 13 millimeter rainfall per year. The Stenocara beetle is able to harvest water on its bumpy back by a combination of hydrophilic or wettable areas on a hydrophobic or non-wettable background. So what happens is early in the morning, when the dew-enriched fog settles over the dunes, the beetle climbs the dune peaks and positions its body in a way that facilitates dew formation. The water condenses on the wettable regions, and once droplets reach critical size, they slide down to non-wettable regions, and the beetle slurps up the water thus formed. Inspired by nature, there are now extensive efforts being made to utilize this as a design principle, and it has been already successfully replicated for fog interception to provide clean water to human settlements in arid regions. These technologies rely upon fog water droplet deposition onto nylon mesh or Teflon fibers. These materials allow condensation of droplets on their surfaces, but resist complete wetting. Schemes of this kind have been successfully implemented in desolate desert areas in countries including South Africa, Namibia, and the Atacama Desert in northern Chile. Several lizard species and tortoises that live in arid areas use similar principles to harvest moisture from humidity, fog, dew, or rain. Bodies of lizards such as the Australian thorny devil, Arabian toadhead agama, and the Texas horned lizard have independently developed body surfaces that are covered with honeycomb-like structures that render the surface superhydrophilic, and increase the condensation of air humidity by about 100%. The water spreads and is soaked into the capillary system in between scales, which transports the water to the mouth where it is ingested. The combination of superwettability, microornamentation, and the semitubular capillaries allows for passive or directed water transport for their survival. Do not mess with these guys, especially the last one on the right. Indigenous plants found in arid and semi-arid locations readily cope with insufficient access to fresh water. Fog episodes occur frequently in many of these regions and help to augment the water supplies for native botanic species through dew and fog collection as well as water vapor absorption. In addition to the adaptive characteristics that minimize the water loss, some species appear to use fog as an additional water supply by using spines that fulfill multiple functions. The bunny ear cactus, shown here, has an efficient fog collection system composed of well-distributed clusters of conical spines. Each spine has 3 integrated parts that have different surface structures and different roles in the fog collection process. The fog collection ability of these and some other cacti is believed to be driven by the gradients in free surface energy and the so-called Laplace pressure. The surface wetting properties are a combination of surface chemistry and surface structures. Their underlying benefits are manifold and range from prevention of settling of pathogens to ensuring floating ability in aquatic plants to facilitating the catching of prey by carnivorous plants. In 1997, 2 German scientists published a paper on the purity of sacred lotus and described what later became known as the lotus effect. If you take a close look at the surface of a lotus leaf, you'll discover a double layer of textures. Waxy microscopic bumps are covered in nanoscale-sized hairs, which strap a thin film of layer. When the rain droplets touch the lotus leaves, they remain spherical, which allows the droplets to bounce around until they fall off the leaf, which stays dry and clean. This self-healing effect can be also found in other species, plant species, birds, and even insects. This phenomenon has aroused great interest for its potential for applications in self-cleaning materials in a number of different fields. A deeper knowledge on how these surfaces attain the property, which is now referred to as superhydrophobicity, is key to reproducing this natural effect in glasses for windows, clothes, and other materials. A particularly important application of this effect is in preparation of self-cleaning superhydrophobic coatings for solar cells, which could solve a major problem with decreased efficiency of solar cells over time, especially in arid regions which are also endowed with highest insulation. You will be surprised to know that there are plants out there that do not even require soil to survive. Perhaps you're familiar with the so-called air plants, such as the Tillandsia, which are biologically referred to as aerophytes. These peculiar plants make good houseplants due to their minimal water and soil requirements. They obtain moisture and nutrients from the air and rain. They usually grow on other plants, but are not parasitic on them, and some can even live on mobile sand dunes. So I did bring some of these plants for you, and you will notice something that is not characteristic for other plants, which is the shape of the leaves. So they have very narrow leaves, shaped like a trough, and this serves for collection of water. There you go. So we can possibly learn something from that and make similar systems that can be efficient water collectors, especially based on the shape of the leaves and the surface of these leaves. Going to the next slide, nature has devised mechanisms for active locomotion of plants, typically observed with rapid movements for prey and defense, or with very slow movements during the growth. One of the frontiers of the contemporary material science research is the design of a new advanced actuating materials which mimic the motility and are capable of fast, reversible, and controllable mechanical motion in response to external stimuli such as heat, light, magnetic field, or electric field. The research efforts in this field are driven by the potentials for utility of such motion to perform mechanical work which could have far-reaching technological implications as mechanically active elements, for example, in the future micro and nanorobotics, which will be soft, organic, and human-like. The remarkable ability of geckos to climb vertical walls and ceilings has inspired philosophers, scientists, artists, and laymen for over 2 millennia. Aristotle noted the ability of geckos to run up and down in a tree, down a tree in any way, even with their head downwards. Geckos use millions of adhesive hairs on their toes to climb vertical surfaces at speeds of over 1 meter per second, which is about 2 miles per hour. Climbing presents a significant challenge for an adhesive in requiring both strong and firm attachment and easy and rapid removal. The attempts to mimic the gecko toe pads is one of the endeavors of the fascinating field of evolutional nanotechnology, which focuses on developing new functional and smart materials by utilizing design principles that have been developed throughout the evolution in nature. The impressive adhesive properties of the gecko's toe pads have been attributed to the nature-salient design of hierarchical biological structures, realized with fine hairs on the gecko's feet, which results in an unmatched demonstration of the power of adhesion. Gecko toes are now well studied, and their sticky properties have inspired some incredible technology, such as stitch-free ways to seal wounds and sticky handheld paddles that may help soldiers scale walls someday. The fascination with the mechanism of adhesion has resulted in several attempts to develop and test new synthetic dry adhesive materials inspired by the gecko toe pads. However, the ultimate goal of creating a perfect mimic that would reach the performance of natural gecko foot hairs has not been accomplished yet, which has even brought dispute over the originally proposed mechanisms of adhesion. To disseminate, some plants have become capable of active migration by reversibly changing their shape and have developed systems to disperse by creeping, crawling, ratcheting, buckling, and slithering. Other plants have developed mechanisms for passive motility, where their seeds can snap, buckle, or explode to disperse, or burrow themselves in the soil in response to periodic changes in humidity or temperature. Hydro-responsive plants, for instance, utilize fluctuations in aerial humidity to enhance seedling survival and represent an alternative approach to environmental energy transduction because the hygromotility does not require light or heat and is driven by slow diffusion control processes that elicit reactions on longer time scales. A multitude of approaches to realization of biomimetic actuating moving devices has been advanced through the design of single molecules, polymers, and composites, where external stimulation by heat, light, humidity, or magnetic or electric fields induces structural changes to drive microscopic motility. When in arid conditions, some grass awns commonly undergo torsional motion for burial. For example, the awns of grasses such as the needle and thread grass are effective drillers that are capable of self-cultivation by propelling themselves into the soil. Resurrection plants such as the spike moss are famous for the ability to survive extreme dehydration and desiccation. During the dry season, the branches curl inwards, forming a dead-looking ball. When dehydrated, the plant can be uprooted and become tumbleweed that blows along the ground with the wind. When moistened, the plant is coming out of the dormant state, induced by the severe dehydration, and opens up. In my lab, we have used some of these principles to prepare materials which are able to drill and burrow themselves into the surface in response to periodic changes in humidity. In the example shown here, we have prepared a material that mimics this behavior and can open and close reversibly when it is exposed to water. It can also feel the presence of a human and can move autonomously by using only the gradient in aerial humidity. Such hygroscopic materials have the advantage of long-lasting, irreversible actuation in absence of light and without thermal or photochemical degradation. Prospective applications range from power generators and smart textiles to artificial muscles and sensors. Some of the most fascinating phenomena that have inspired biomimetic research are related to the ability of living systems to use or to generate light. Light is eternal but ethereal. Light does not require contact and therefore provides means for a remote control to biological or artificial systems. Light interacting biological structures reflect the uniqueness of the nature's optical design, but they also suggest broad innovation in nature's use of materials and its manipulation of light. And if we can just have the lights dim, please. This is our planet, and if you look very closely, you might see a strange blue glow off the coast of Florida when Florida comes into the picture. This bright blue glow in the ocean is produced by a subgroup of algae called dinoflagellates, which are the main eukaryotic organisms that are capable of generating cold light. So that would be somewhere here. You can see this glow. When their population are dense, the disturbance of the water during night causes bright blue bioluminescent displays that have been reported since at least 500 BC and are known to occur globally. Bioluminescence, the phenomenon of biological generation of visible cold light by the excitation of chemically produced excited states, has been documented as early as Aristotle's De Anima, about 350 BC. It has inspired chemists, writers, artists, and laymen for thousands of years. It is displayed by a number of organisms, including certain species of bacteria, insects, jellyfish, mushrooms, worms, and squid. There are about 70 biological families of lower organisms spanning over 250 genera, which are known to display bioluminescence. Only the family of beetles known as fireflies, for example, contains 5 genera and about 2,000 species. So in the bioluminescence world, the core physical process of this natural phenomena is energy transduction, by which living organisms use enzymes to convert the chemical bond energy of ground state reactants for electronic excitation of the reaction products. The chemi-excited products subsequently emit light in the visible region of the spectrum, which is used to communicate signals. The bioluminescence is used for communication, prey, of defense. So in the bioluminescence, there are these creatures, such as the sea slugs, which are the good ones, and there are the bad ones, such as these dragonfish, and of course, there are the ugly ones. And this would be the ugly ones. The type locality of this worm, called Diplocardia longa, is a small town in Georgia in the US. Its body fluids and the sticky slime that the worm secretes when stimulated emit a bluish glow. The nature of the emitting chemical species, however, remains uncertain. Also, there are the scary ones as well. So this fish, known as Photoblepharon, uses luminescent bacteria under its eyes. You don't want to meet this guy in a dark alley. But it is scary because it's really tiny and harmless. So the light or the bioluminescence has been utilized and provided an irreplaceable analytical methods for precision on a picomole range. This is 10 to the minus 12, and evolved into one of the first non-invasive methods for visualization of cell and tissue organization. The bioanalytical techniques based on bioluminescence have become some of the most versatile and powerful analytical tools developed in the 20th century. They are nowadays extensively used for in vivo imaging, for monitoring of cell proliferation, protein folding and secretion, environmental research, food quality control, and protein and genetic engineering. The bioanalytical techniques based on bioluminescence are sensitive, reliable, quantitative, rapid, non-invasive, and generally come with a high signal-to-noise ratio. However, some of the most recent biometric applications in material science are focused on the firefly lanterns, which help to very efficiently uncouple the light from the body and to deliver strong optical signals in sexual communication. The high transmission nanostructures of the firefly lantern cuticle have become biological inspiration for highly efficient LED illumination. Such biologically inspired LED lenses substantially increase the light transmission over visible range compared to conventional anti-reflection coatings. One of the most remarkable consequences of the orders and patterns that are generated spontaneously is the so-called structural color. The description of these optical effects is as old as the Robert Hooke's famous book Micrographia, published in the 17th century, where he presents microscopic images of brilliant feathers of peacocks and ducks and reports that the colors of their feathers are destroyed by a drop of water. When a matter is illuminated with white light, we see color only if the reflected light is of particular wavelength that is detectable by our eyes. There are two ways to eliminate the remaining wavelengths: by absorption, as is the case with colored materials such as pigments, dyes, and metals, where the color is due to the exchange of energy between the light and electrons. In the second case, the light is reflected, scattered, and deflected, and it doesn't reach the eyes because of the physical phenomena that happen on the specific surface structures. In nature, these colors are enhanced by thin film and multi-layer interference, diffraction gratings, light scattering, or photonic crystals. So if you look at these pictures, you see the different structures in the blue region here than in the green region. And there is a further degree of complexity, because if you zoom in these structures, you will see even tinier and finer structures that actually all contribute to light without any pigmentation. Some insects and butterfly species use similar complex photonic bandgap structures that prevent propagation of a band of wavelengths through them and thus cause very strong colored reflections. In butterflies, such as the blue morpho butterfly, the visibility of up to 1/2 mile is attributed to photonic structures that are formed by discrete multiple layers of cuticle and air. The butterflies use light-interacting structures on their wing scales to produce color. The cuticle on their scales is composed of transparent chitin and air-layered structures with size from the nanoscale to the microscale. These multi-scale structures cause light that hits the surface of the wing to diffract and interfere. Cross strips that protrude from the sides of the ridges on the wing scale diffract the incoming light waves, causing the waves to spread as they travel through spaces between the structures. The varying heights of the wing scale ridges affect the interference such that the reflected colors are uniform when viewed from a wide range of angles. The specific color that's reflected depends on the shape of the structures and the distance between them. This way of manipulating light results in brilliant iridescent colors, which butterflies rely upon for camouflage, thermoregulations, and signaling. So before I go on to the last part of my talk, I would just like to briefly introduce two last examples that come from faculty who are now here at Harvard, where there is a very active research in this biomimetic field. The first is a sessile deep water sponge known as a Venus flower basket. It's called Venus flower basket because it has a couple of shrimps that remain trapped there forever, for life. So this is a symbiotic organism. This impressive structure was studied by Joanna Eisenberg here at Harvard, and although it is essentially made of the fine fibers of glass with diameter close to the that of a human hair, it can withstand enormous pressure at the sea floor due to its specific hierarchical structure which embodies reinforcements at multiple levels. The second example comes from the laboratory of Lakshminarayan Mahadevan and explains how tendrils of cucumbers and some other plants work. Once it is attached to a solid surface, the tendril shortens into a helix, pulling the plant. But rather than twisting in only one direction, which is impossible without twisting the plant on the other hand, the two halves of the coil section curl up in opposite directions, separated by an uncoiled stretch, so there is no net twist. In addition to being a significant component of a bio-inspired architectural design, a portion of the biomimetic research is proprietary to specialized national defense labs that develop stealth technologies and is not available to public. The stealth or low observable technology covers a combination of techniques that range from aircraft shape to special low observable coatings that are used to make personal or military objects or vehicles less visible or invisible to radar, infrared, sonar, and other direct detection methods. The very early stealth technologies involved the concept of camouflage for reducing the visual signature by making appearance of an object blend into the visual background. Increased capability of the detection and interception technologies required advanced materials that either deflect or absorb electromagnetic waves from tracking devices. For example, central to the design of the F-35 Joint Strike Fighter design is the application of composite materials such as composites of fiber mats and polymers to reduce observability and maintenance costs, while avoiding applications of stealth coatings. Future increases in human welfare will be driven by the increased understanding and mastery of the natural world, and the materials scientists are posed to expand the frontiers of human knowledge by exploring these secrets. But the globalization has a dark side too. We're living in an urban century, and demographic forecasts indicate that world population will reach 9 billion by 2050, which is an increase of 2 billion than at present. Being a phenomenon of physical and cultural restructuring, the globalization will have complicated and far-reaching social, aesthetic, economic, and physical and political effects. Environmental challenges facing the planet are complex, and their impact on the natural world and on human society can be catastrophic. Climate change, loss of natural resources, declining biodiversity, deforestation and desertification, changes in the carbon, nitrogen, and phosphorus cycles, sea level change and pollution each pose enormous problems both regionally and globally and indicate a dystopian future. So on this slide, you can see some of the species that are already extinct or close to extinctions. These challengers are intricately interwoven with issues of human health, population, migration, water, food, and energy security, and inevitably the potential for conflict. They require a broad interdisciplinary approach to understand them and to provide solutions. Many of these challenges already have had or will have direct impact locally. Our planet is now in the midst of the 6th wave of mass extinction of plants and animals in the past 500 million years. We are experiencing the worst state of species die-offs since the loss of dinosaurs 65 million years ago. It is estimated that we are losing species 1,000 to 10,000 times the background rate, which is 1 to 5 species per year. This slide that I showed shows only a few of these species that are close to extinction or extinct. And this is only a small fraction of the species that we are aware of. There are many more species, both small and big, that are lost forever without us even knowing that they ever existed. So there are several questions that I will pose at the end of my talk. Can we reverse this process? Can we prevent, slow down, destroying, or remedy nature while continuing to increasingly explore its resources? And does humanity really need a backup planet? Thank you.